Our goal at the moment is to understand algorithmic state machine timing. So the first thing to understand is that init doesn't happen inside this box. Init happens on the rising edge of the clock that moves us from algorithmic state 1 to algorithmic state 2. So right here in this area of the line is where init actually happens. Right here is where decrement and add happen. In this line is where shift right and complete happen, whatever complete means, signaling back to the original computer that you're done. In this line right here, just shift right occurs. And in this line, nothing's happening. This is the idle state. So there's a difference between what goes on in this line and in this line. So the question then is, what are these? Well, we've defined them as outputs, but you need to think of them as a wire that is true or false. It's a 1 or a 0. It's on or it's off. It's set or it's not set. That wire has to be set before the clock tick occurs. And that wire's value triggers this init. We set this wire decrement. It's a wire coming out. And that wire's value triggers the decrement down here. Adds value triggers whether we add or not. This path we're not going to add. This path we are going to add. This wire right here toggles shift right. And this one is a wire that toggles complete. So the outputs of our algorithmic state machine are telling other circuits what to do. They don't do it themselves. Now I'm going to talk about the inputs. We have an input right here, but it's the clock tick right here where it looks at the input. So S has to be set up and hold its value through this clock tick. M1 has to be set up right here and it's looked at right there. Z has to be set up right here and it's looked at on this clock tick, not on the clock tick out. So in our algorithmic state machine, it looks at our inputs, adjusts the outputs, and then leaves on a rising edge of a clock where actually shift right and complete happen. So these have to be set up before the transition to where they're looked at. So let's draw a clock pulse. This is the rising edge. It's going to trigger things from happening. Over here we have our algorithmic state machine. Here we have our Mealy and Moore circuits. So during this clock period, the algorithmic state machine is looking at inputs and it's deciding what to do next. And it's got to get all that stuff done before this next clock pulse. The Mealy and the Moore circuits are doing stuff like shifting right, adding, decrementing, initializing. And they're setting up inputs that trigger the algorithmic state. And that's all got to be done by this clock cycle. And then we just get a repeat here, and it keeps going forever and ever. What messes all this up, the evil thing that messes all this up, is async. Async is bad. Where does async come from? Built in chips. It's built into chips, even the virtual chips, the ones you find in your simulator. They're making decisions in here. This stuff's happening in here at the speed of light with these async chips, and it ruins everything. Everything has to be synchronous, happening on this clock pulse, in between, on this rising edge of the clock pulse, in between these algorithmic states, in between these mealy or more states. Next, we're going to watch an algorithmic state simulation and a mealy and a more, and your goal is to watch the timing of it. I'm going to try to describe it, but you might want to play sections over and over and over again. So this is our finished circuit. I've got two versions of it. One's with a purely synchronous counter. That's this circuit over here. And the other's with a asynchronous counter that has problems. But let's just go through this circuit and map it to these drawings we've been investing time in. This is right here. That's our algorithmic state machine. Can't see the circuit yet. This counter, which looks like the most simple thing, which is actually the most complicated, is right here. And this is all this other stuff. The three of these combine to make this entire circuit, and I'm going to demonstrate it now. So what we're going to do is multiply 3 times 6. Right now, the algorithmic state machine has 2 flip-flops because we have 1, 2, 3 states. The counter has 3 flip-flops because it's counting up from 0 to 4. We're going to start off by making it 0 and toggling through a 0, making sure we stay at the 0, 0 state. Right up here, we stay inside this state. And now we're going to start the process by making S right here a 1. So this is something that the computer does. Click 1. And now init's been set. Right here, init's been set. Init is this wire right here. And it goes up to init inside the shift register, and it goes to init right here in our counter. So now we're actually going to do the initialization, and we'll see this counter go back to 0. There we go. So that's the clock pulse in between these two. Now we can see that we're in state 2, and the more decrement has already been set up. There's our decrement, and it's going to go out here and decrement our counter. We're actually incrementing it. All right. So now we're going to click the clock. It looks like M1's value right now is 0. M1's coming right out here and is going back into our algorithmic state machine. So our algorithmic state machine right here is seen as 0 coming in. And we counted 1. So in that clock tick, we moved from here to here, and we decremented, because you remember the decrement occurs in between these two states. So that's why we got the decrement here and not earlier. All right, remember we're playing the role of the computer that's executing an assembly language command. And we put the numbers, we being the computer, put the numbers 3 up here and 6 here. Now this has already started, so we should be able just to go through here and toggle these guys off. Now for our purposes, we need to remember that it was 3 times 6. So this answer here should be 18. If we look at our algorithmic state machine, we should see a set of the shift register wire to true. And there it is. That's the shift register wire. Shift right. So that's going to happen on the next clock pulse. And because Z's right here is 0, we should be going back up here to state 0, 1. Currently we're at state 1, 1. So we should see this 1, 1 change to 0, 1. We should not see any kind of counting here. And we should see this 1 move to there and that 2 move to here. All right, here we go. Yes, we saw the shift occur right here. We saw ourselves going to the second algorithmic state, going back to it. And now we're ready to decrement again. That's set up by the more circuit. There we are decrementing. And it looks like this time M1 right here has been toggled so that we're going to actually add. Now we can't see the results of the add, but they're right here. This is 0, 1, and 2. So that 0, 0, 1, 1 is going to move into here when we click the button, and this is going to increment. So the 0, 0, 1, 1 moved into here, and we moved back down here to state 1, 1. The shift is set. So Z is still 0, so we're going to go back up to here. So we're going to go from 1, 1 back to 0, 1. And we're going to shift right. So that 0 is going to disappear. And these two, this one's going to move to there, and that 0 is going to move to this 3 line. Yes. I trust that you're going to get this circuit downloaded and play with it and talk yourself through it like I've been. But right now what I want to do is just bang on it and see if we get the answer. So I'm just going to hit this until I see done. Done! 16 plus 2 is 18. So 3 times 6 is 18. Yeah. So we have 4 circuits here. We have this big overall circuit. We have the algorithmic state machine circuit. We've got the register circuit. And then we have our counter circuit. So we're going to go through them. We've just finished going through the big one. So we're going to go through the algorithmic state machine. We're just going to glance at it, talk about it a little bit. And then the shift registers, which we've already seen. And finally the counter. So here's the algorithmic state machine. The key thing to look at is its organization. Here are the 2 flip-flops here in the middle. Here are most of the outputs. Here are our inputs, and then this is the clock. Now S comes from the computer, and because we're operating this by hand, I had to design this little circuit right here to modify S's behavior so that S was only a 1 inside this state and 0 everywhere else, no matter what you did as a user banging on the overall circuit. And then I had to modify M1 with this gate so that it would only wake up here in algorithmic state 2. And then I had to modify Z right here so it would only wake up when we're going out this mealy path. So those are the major issues associated with the algorithmic state machine. And then just setting up the flip-flops right here. These are the 2 registers coming from the computer that I cleared in the example so that the computer can reuse them for other purposes. They just need to have accurate data in them. We had 3 in one and we had 6 in the other, and they just need to be there for the first initialization that copies their data into these internal registers right here. So these external registers that the computer used to load them are freed up. And here we see the 2 internal registers right here. These are these registers A and M. And then we have the register B down here, right here. We have our flip-flop right here. And then we have our adder right here. Okay, so those are the landmarks here in our register circuit. And then here we have the counter circuit. The counter circuit is a problem because if you try to use the simulator's counter, it has this asynchronous input right here. So what I did is I redesigned the entire counter from scratch as a Moore machine. You can see the output is just dependent upon the flip-flops. So I had to draw a state diagram for this finite state Moore machine. So we started off right here. I've got my counter going through a 0, 0 state. That's its output. And then if it receives the decrement, so I've really got 2 inputs into this, decrement and init. My pairs are going to be decrement, comma, init. When I get a 1, 0, I'm going to go here and increment. Now, if I don't get anything, I'm just going to stay at this spot. This is going through algorithmic state 3. Now at this point, this 1 right here triggers Z. This third 1 triggers Z. So we're going to go out here on this complete path and stay here at this state. So Z has to stay a 1 through the clock tick between algorithmic states 3 and 1. And we're only going to get out of there on an init. It's on a 0, 1. And then all the other possibilities, like a 1, 1, 1, 1, 0, 1, are all going to go back here. So that's the state diagram that was used to build this circuit. This is the circuit used in the animation shown earlier. But that was just another finite state machine, something we've talked about in Chapter 7. The major points here are about algorithmic state machines. And let's just review. Nothing really happens inside one of these algorithmic states. Everything happens in between. Right in here, and in here, and in here, and these feedback lines. Mealy and Moore just set wires. These are our outputs of our algorithmic state machine. So the Mealy inputs are S, and they have to be locked into these algorithmic states. Otherwise, Z starts getting looked at right here and influencing things. Async is evil. Async actually causes things to happen inside these algorithmic states. Now we're going to go through the process of turning this algorithmic state machine into a circuit. The steps are similar to a finite state machine. In some ways, even simpler.